one thing. Whenever you're doing Euclidean geometry, you don't have to panic. Think of theorems. These become your key to unlock any Euclidean geometry problem. Before I even look at problems, when I look at this, I see what? I see a diameter. Do I know any theorem that deals with a diameter? Ah, this is the one. So I check where the diameter goes. It forms that angle, which will be 90 degrees. So we already know some of the things here. Since I have a diameter here, it will form this angle, which is 90 degrees. So that angle will be 90 degrees. I definitely know those things. Right, what else do I know? Ah, what is the name of this line here? Remember, this is our tangent. What is the name of this line? Line MD. This distance from the center of a circle to the circumference. It's a radius. Do I know any theorem that deals with the radius? Yes, this is a radius. Whenever it meets the tangent, it will give us 90 degrees. So I look for those things. Those will be my solutions. Look at this one. From there to here, so this angle here is 90 degrees. I know it is 90 degrees because there's a tangent that is meeting a radius. This other side also will be 90 degrees. Tan radius theorem. Right, and so on and so forth. But let's look at what we have here. We are also told that MB is equals to 2BC. Where is MB? MB is equals to 2BC. So in other words, this distance, it's 2 times this distance. I've just indicated in that way. So because MB is 2 times BC, so BC is half of MB. Right. Remember what is this? This is the diameter. If this is 2 times, this side will also be 2 times because this is also a radius. Another thing that I indicate here, this distance from there to here is the same as this distance from here to here. What do we call it? We call it a radius. The line from the center of a circle to the circumference. Circumference. It's the same distance. Therefore, we know that this distance is the same as this one. As I do that, something should click. My grade 8, grade 9 Euclidean geometry. The types of triangles. So I know exactly what type of a triangle this one is. It's an isosceles triangle where these two are the same. Therefore, these base angles will also be the same. So I know that this angle is equal to that angle. Let's look at questions now. The question there we are required to find if angle D is equal to, if angle D4, where is D4? This is where D4 is. We're told that this small angle there is equal to X. It is equal to X. That small angle there is equal to X. Where is that angle? This angle is between a tangent. Do you see this tangent? It's a line that touches the diagram at one point. It is between a tangent and what? What is the name of this line? It is called the chord to the circle. It divides into a smaller part of a circle and a bigger part. So there's an angle that is between a tangent and a chord. Do I know any theorem about that? Yes, we do. An angle between a tangent and a chord is equal to the angle subtended by that chord in the alternate segment. So I know that if this angle is X and it is between a tangent and a chord, I've got to use the chord and go where? Not just anywhere, I go to the circumference. I cannot simply from here and move to this one. Yes, this chord subtends this angle, but not at the circumference. It is important that we should go to the circumference. So from here, I go to the circumference. Hence, this angle X will also be equal to this angle X. This is another angle that is equal to X. Remember, we're required to find how many? 2 angles. This is about 3 marks in the examination. We found the first one. What theorem did we use? We used the tan chord theorem. So angle X is equal to angle A. That's one angle that is equal to X, 2.1. It's X also, angle A is also equal to X, which is one of them. But once we find that this is also angle X, we can also see that since this triangle is an isosceles triangle, therefore angle D2, we can also refer to it as angle X. These are the 2 angles that we can call angle X as well. Remember the first one? We just use nothing else but our theorems. Tan chord theorem, go to the circumference, find that angle X is equal to this one, you state the reason, tan chord theorem. Number 2, you use this triangle here. This is an isosceles triangle, triangle AMD. This is the triangle that I'm talking about, triangle AMD. In this triangle, these 2 sides are equal, therefore these angles will also be equal. Therefore, this other angle, if this is X, this one will also be equal to X. That's how we go about responding to 2.1 for about 3 marks in our examination. This is a November 2000, no, this is an exemplar 2014 paper. Look at this next one. 2.2. Let's write it down. 2.2. 2.2. Prove that CM is a tangent. Where is CM? Prove that CM, this line. Remember, this is the same line. Prove that CM, remember, this is the same line. Prove that CM, I repeat again, remember, this is the same line. Prove that CM is a tangent. It is a tangent at M. CM is a tangent at M to the circle passing through MED. There's a circle that passes through MED. Let's put that circle there so that it will give us a clear picture. MED. So there's a circle that passes through that where this line is a tangent. Let's do it. MCD. It passes through here, there. There's a circle that passes through there. All that we need to prove there is to prove that this line is a tangent. CM is a tangent. Right. Let's check here. Which theorems deals with the tangent here? These are the three. All right. It deals with the tangent. What do we know? We know that, let me just show you here. If this is a tangent, all right. Okay. Let me look at, oh, there's a straight line. So I've used a straight line. When I use this theorem, if this is the circle, what happens here? Suppose I don't know the name of this line. I know this one is a radius, or maybe I don't even know it. But whenever this angle here that is formed here is 90 degrees, I will definitely know the name of this line and the name of that line. If this angle here is 90 degrees, it will call us to know that this line is a radius and this one is a tangent. So whenever I've got a situation like this, whenever I've got this one from the center, this angle, if this angle is 90 degrees, definitely that one will be a tangent. Or if this angle is equal to that angle, therefore definitely this line will be a tangent. So I've got, I can play around with those two because those are the theorems that deals with a tangent. All right, let's do this thing. Let's look at what we have here. Okay, we've got to show that CM, this line, CM is a tangent. The only way to do that is to show that this angle here, if an angle that is here is equal to that angle, therefore this line will be a tangent. That's what we're doing here. Let's do this thing. Now watch here. What do we know here? What do we know here? Let's call this a chord. Let's call that a chord. Okay. There is this angle. This will be our tangent. We don't know it yet. This will be our tangent, this line. If this angle here, that is between a particular line and a chord, this angle M3, how many degrees is M3? It is 90 degrees. Let's go to the chord. If you go to the chord, if this angle, this one, is equal to the angle subtended by this chord, then these two will be the same. Hence, this line will be a tangent. Now, when we come to this chord here, there's an angle that is between this line, which we don't know what it is, and this chord. Now, when we move with this chord and we go to the circumference, we move to the circumference. What angle is formed here? This angle is 90 degrees. And what is the value of this angle that is between the tangent and the chord? It is also equal to 90 degrees. Therefore, this line will definitely be a tangent. Let's write it down. We are saying angle M3 is equals to 90 degrees and is between a tangent, is between a chord and a line, which we don't know at the moment. Let's call it line MC or AC. In this case, they use CM, which is the line between CM, or the whole line, which is AC, which is between AC. Right, let's move on. So we know that M3 is equal to 30 degrees. It is between a chord. What is our chord here? In this particular case, our chord is ME. The one that we're talking about is ME. We take ME as a chord in this particular circle. Right. This chord subtends a particular angle. Now, this chord subtends angle D at the circumference. Now, if that happens, now our chord ME subtends forms angle D, what is this? It forms angle D, which is equal to 90 degrees. And we can see that this angle that is between this line and the chord is also 90 degrees. So if these two angles are the same, they are equal. The angle between a particular line and the chord is equal to the angle in the alternate segment. Therefore, we can safely say that this line will definitely going to be a tangent. Right, that's how we'll go about doing question 2.2. We say ME forms angle D at the circumference, which is equal to 90, as well as the angle, this angle M3 is also equal to 90 degrees. Therefore, line AC, line AMBC, the whole line, AMBC. Therefore, line AMBC is a tangent. And this line, line CM, is part of that line. CM is part of this whole line. Therefore, line CM, they call it CM, therefore line CM is a tangent. The idea was to use the theorem to know that if I've got an angle that is between a particular line, it is equal to that one, therefore this line will definitely going to be a tangent.